The strategy of inference time scaling has established a clear trend. Ensembles of small large language models can now regularly outperform single monolithic frontier models. This diagram outlines a standard mixture of agents pipeline. A single prompt is routed to multiple independent LLM nodes, the proposers. They generate their own independent answers. These individual outputs then converge on a single aggregator model, tasked with synthesizing the variations into one final response. But this baseline architecture relies on naive text concatenation. The proposer outputs are simply dumped into the aggregator's context window. There is no structured mechanism for the models to interact with or critique one another's reasoning. If one proposer generates a highly persuasive but factually incorrect hallucination, it often bypasses the aggregator's limited scrutiny and infects the final output stream. In deep, multi-layer systems, this problem compounds. Unverified errors cascade and amplify as they pass through successive aggregation stages. Naive text concatenation guarantees that the error introduction rate eventually overwhelms the system in complex logical tasks. Attention MoA is an architectural framework designed to mitigate this unverified error propagation. It replaces direct text concatenation with a mechanism called inter-agent semantic attention. This split-screen comparison illustrates the difference. On the left, traditional transformer attention uses a mathematical formula to apply numerical weights between embeddings. On the right, semantic attention translates this concept into natural language, outputting a readable English sentence that critiques a specific logic step. It forces the models to generate explicit instructions, creating an adversarial peer review process before any aggregation occurs. Attention MoA structures the interaction so that models use natural language to audit peer reasoning before any final synthesis occurs. This is a spatial reasoning case study from the FLASC benchmark. The board state shown here requires a precise checkmate in one move. The solution requires strict adherence to physical spatial constraints, specifically recognizing which pieces block the paths of others. Looking at the logic tree generated by the standard mixture of agents baseline, the system ultimately selects the move queen to g1 check, highlighted here in red. The models hallucinate an illegal move because queen to g1 check sounds structurally plausible in natural language, even though the board layout makes it impossible. Standard models use constructive logic to build a path to an answer. They lack a discriminatory mechanism to actively evaluate and reject competing errors. When an aggregator faces multiple confident proposals, lacking a way to reject errors leads to failure in high-stakes reasoning. This flowchart illustrates the first stage of the attention MoA fix, heterogeneous agent sampling. A single query branches into parallel agents, each generating its own independent response. This setup ensures the initial pool captures a wide diversity of perspectives, including both correct answers and potential hallucinations. The system then pauses generation and begins critiquing through a cross-attention mechanic. The parallel agents establish an advisor and recipient relationship with one another. Agent A, acting as the advisor, uses its generated response as the query vector. It runs this against Agent B's response to systematically identify discrepancies and logical gaps. Instead of a numerical score, Agent A outputs an explicit corrective instruction in natural language. In this text document visual of the chess problem, Agent A evaluates the illegal move. It flags the text queen to g1 check and generates the specific peer critique. Invalid, the bishop on f1 blocks this path. This specific cross-attention step provides the discriminative logic required to isolate and reject the hallucination. Cross-attention leverages the diversity of the ensemble, forcing models to act as reviewers to catch logical blind spots before consensus is attempted. Following peer review, the system initiates a secondary phase, self-attention. The agent evaluates its own initial draft to identify internal contradictions, generating a self-refinement instruction to correct its own errors. In this visualization of the synthesis phase, the recipient agent collects all incoming semantic instructions from peers and its own self-attention and combines them. The agent processes this feedback through an update function to generate a revised, corrected response. Finally, these revised response nodes feed into an intra-layer summary agent, which acts as the projection layer to output a single, unified block of text. Unlike standard mixture of agents frameworks, this summary agent builds its consensus from reasoning that has been rigorously audited at the local level. Looking at a macroscopic view of the complete architecture, we see how the system scales by stacking these semantic attention layers sequentially. Deep LLM architectures face a risk of information degradation. Critical context is often lost as data passes through multiple summarization bottlenecks. To prevent this, Attention MoA introduces an interlayer residual module. This bypass pathway aggregates historical context, ensuring the model retains the incremental improvements made in earlier layers. The residual module also incorporates an adaptive early stopping mechanism that continually evaluates the stability of the reasoning trajectory. Once a logical consensus is reached, this early stopping mechanism terminates redundant iterations. This saves roughly 11% in inference token costs, while preventing over-reasoning. This bar chart presents the empirical results of the framework against current state-of-the-art models. Attention MoA achieves an MT bench score of 8.83, exceeding both Claude 4.5 Sonnet and GPT 4.1. The Attention MoA configuration achieving these scores is composed entirely of small open-source models operating in the 12 to 32 billion parameter range. This radar chart maps performance across Flask dimensions. Attention MoA establishes a lead over standard mixture of agents in critical cognitive and safety metrics. This performance gap suggests that the semantic attention module identifies and intercepts logical inconsistencies that baseline aggregation ignores. The entire AI industry focus is now rapidly transitioning from raw parameter count to the architecture of inference time collaboration. Advancing AI reasoning relies on engineering communication topologies that force models to scrutinize and refine logic during the generation process.